So here's a similar situation. I once again am confronted with a series that I don't know anything about, and I want to know if it converges. I can look at some of the terms if I want. You don't have to, but it can sort of help you to see what's going on. I can see, for example, that this is not geometric or p-series, and I can sort of observe that the limit as n approaches infinity of a sub n equals 0. I can sort of see that, or I can make a graph. If you wanted to rigorously prove that the limit as n approaches infinity of a sub n is equal to 0, it would not be hard. You would use L'Hopital's rule on this and you would get it right away. But you don't have to. As long as we are reasonably sure that the terms are going to 0, we're going to proceed with some other analysis. So what we're going to look at on this one is we're going to say, well, this one, it has a power of n in the top and a power of n in the bottom. And so it's really more p-series-y than anything else. It's sort of p-series-y. So let's compare it to a p-series. How would square root n over n minus 5 compare to square root n over n, which is a p-series because it would be 1 over square root n, which is 1 over n to the 1/2. A p-series with p less than 1, which we know converges, right? So this one, diverges, right? So if this were a series, it would diverge by p-series, I should say because it's a p-series with p less than 1, all right? That's what would happen to these things. How does this compare? Well, I'm subtracting something off the denominator. That means that these terms are going to be larger than those terms. But by the way, only for n greater than 6. Because if n is less than 6, if n is, well, really I should say n greater than 5. I could say n greater than or equal to 6, right? N greater than or equal to 6. All right, because if n equals 5, this is undefined. If n is less than 5, so for 1, 2, 3, and 4, they're natural numbers. They're part of the domain of sequence, but they would make these terms negative, and therefore they would be less than these terms, which are all positive. So this only works for n greater than or equal to 6. So isn't it convenient that whether you noticed or not, I wrote the sum from n equals 6 to infinity. Now, so the questions of convergence are all going to be similar. I can exclude finitely many terms, and the convergence or divergence is going to be unaffected. So if I'm curious as whether something's infinite or finite. If I take out finite amount from it, it's still going to be the same quality that it was, either finite or infinite. Hopefully that makes sense. All right, anyway. So here's what we have. Square root n over n minus 5 is greater than 1 over n to the 1/2. And I know that sum from n equals 6 to infinity of 1 over square root n diverges. So I wrote this up here, but you need to say the series diverges because it is a p-series with p less than 1. All right, so we're going to say that the sum from n equals 6 to infinity of square root n over n minus 5 diverges by the comparison test. All right, so what happened this time is that the terms that I have are larger than a series that I know diverges. So if I'm looking, at the graph again, so I'm looking at a series that I know diverges, so this area is infinite. And then I'm taking terms that I know to be larger than this divergent term. So I'm taking things that are larger. Well, they're more than infinity, so they're also infinite, right? Because remember, you're taking the full sum in each part. All right, so hopefully that makes sense. And here's what it comes down to with this comparison test that we're using, the comparison test. And noting that the terms of both sequences, the terms of both series, have to be positive. All right, and that's the case here, that as long as n is greater than or equal to 6, this sequence, which you're going to call b sub n, is positive. And our comparison series, which we call a sub n, is positive. So sometimes we call this the b sub n. We're going to call this a test series. And then we're comparing it to something that we're going to call the comparison series. That's what a terminology that we'll sometimes use. It's not like a universal terminology, but it's handy when you're using these comparison series. So you have your problem, that's your test series, and then you have your known convergent series. That's your comparison series. All right, so can we summarize these two conclusions? We can on page 686 of your Stewart-Kokoska, page 686 in section 9.4. The comparison test. Notice that A sub n and B sub n are series with positive terms. They do something nice, which I haven't done yet, but you'll see me do it eventually. They just wrote a sigma. There's no n equals 1 to infinity. So if they don't write n equals 1 to infinity, it's n equals 1 to infinity. So just a shorthand, we're usually only concerned about the infinite sums. And notice how it doesn't matter if it was, n equals 6 to infinity. The convergence or divergence is going to be unaffected by that. So we can just say the sum of A sub n and the sum of B sub n. Sometimes I'm a little sloppy with the words sequence and series. You'll hear me switch those up a little bit. When I'm adding them, it's called a series. If I just look at the list of terms as a list, that's a sequence. So I should not mix up sequence and series, but I sometimes will. By the way, another little handy English lesson here. There are two of these series. The plural of series is series, just as the plural of moose is moose. One moose, two moose, one series, two series. Okay, so suppose you have two positive series with all positive terms. That means all of the terms are positive, all right? If B sub n is convergent and A sub n is less than or equal to B sub n, then A sub n is also convergent. In other words, if your test series is less than or equal to a convergent series, then your test series also converges. If your test series is larger than a divergent series, then that test series also diverges. I guess A sub n is the test, B sub n is the comparison. So if sum of B sub n is divergent and A sub n is greater than B sub n. So you know that a series diverges if all of its terms are greater than a known divergent series. You know that a series converges if all of its terms are less than a known convergent series. Of course, if your terms are less than a known divergent series, in other words, if you switch these inequalities, then you get nothing. You know nothing. We'll see some examples of that and what we'll do about it. If, likewise, you know that you have terms that are greater than a series that is known to converge, again, you have nothing. Greater than convergent tells you nothing. Less than divergent tells you nothing, right? Less than divergent is just saying, I have a number that's less than infinity. Is it infinite? Is it infinite or not? So, well, you have to contend with the fact that, yeah, there are infinities that are less than other infinities. Although that's not exactly how this works. You have to really think about what less than means. So I guess that's not really a good comparison. If you're less than infinity, we don't know what you are. If you're greater than finity, if you're greater than a finite number, you could be infinite or infinite. So if you're greater than a convergent series, we know nothing. If you're less than a divergent series, we know nothing. If you're less than a convergent series, we know you converge. If you're greater than a divergent series, we know you diverge. That is the comparison test. Read it, love it, and recognize this limitation that sometimes you are going to have a series that's greater than a convergent series. And then what do? What's it going to tell you? All right, so there are ways that we can handle that. So that is your introduction to the comparison test. We'll look at a couple examples and some more things.